A conservative force. A conservative force F is in the plus x direction and has magnitude f of x equals alpha divided by x plus x0 squared. So parentheses squared. Where alpha is 0.8 newtons meters square and x0 is 0.2 meters. Part A. What is the potential energy function u of x for this force? Let u of x go to 0 as x goes to infinity. Part B. An object with mass m equals 0.5 kilograms is released from rest at x equals 0 and moves in the positive x direction. If F is the only force acting on the object, what is the object's speed when it reaches x equals 0.4 meters? So this force is a conservative force, therefore it's derivable from a potential energy function. F of x is equal to minus du dx. So we can write the change in the potential energy as minus integral from 0 to x f of x dx. The work done by this force is equal to minus the change in the potential energy, work potential energy theorem. So this is minus integral from 0 to x. For f of x we substitute alpha divided by parentheses x plus x0 squared dx. In order to perform this integration, let's have y stand for x plus x0 so that dy is equal to dx. Okay, now we can calculate the change in the potential energy, delta U, is minus the integral when x is equal to 0, y is equal to x0. So this integral is from x0. When x is equal to x, y is equal to x plus x0. So the upper limit is x plus x0. We have alpha divided by y squared dy. So this integral will give us minus alpha y to the minus 2 dy. So y to the minus 2 will give us a minus 1 y to minus 1. If you take the derivative, you get plus 1 y to minus 2. So that's the integral. And this is to be evaluated between x0 and x0 plus x. So the potential energy at point x minus potential energy at 0 is alpha times 1 over y, so that will be 1 over x0 plus x in that limit, minus 1 over x0. So we evaluate minus y to the power minus 1 between x0 and x0 plus x, and the potential energy should go to 0 as x goes to infinity. This is going to be 0. So if I substitute x equals infinity here, I obtain u at infinite minus u0 is going to be equal to alpha divided by infinity minus alpha divided by x0. This is minus alpha divided by x0. So the potential energy at x equals 0 is alpha divided by x0, and the potential energy as a function of x will be then given by alpha divided by x0 plus x. All right. So this basically ensures that the potential energy goes to 0 as x goes to infinity. And when the x is equal to 0, it's alpha over x0. So these conditions are satisfied by this function. So we obtain the potential energy function u of x is equal to alpha over x0 plus x, where alpha is 0.800 Newton meter square and x0 is 0.200 meters. So this was given in the problem statement, these values. All right. So let's move on to part B. Now, the potential energy at x equals 0 is alpha divided by x0. The potential energy at the final point is alpha divided by x0 plus x final. The object is released from rest, so the kinetic energy at 0 is 0. The final kinetic energy at x equals x final is 1 over 2 mv final square. In this process, the change in the mechanical energy is 0 because we only have conservative forces acting on the system. Therefore, delta K plus delta U is equal to 1 over 2 mv final square, K final minus K initial, plus alpha divided by x0 plus x final minus alpha over x0 equals to 0. So if we solve for V final from this equation, V final can be isolated as 2 alpha divided by m parentheses 1 over x0 minus 1 over x0 plus x final square root. So this is the symbolic answer for V final at a position x final. Now you can see that I have taken these two to the right hand side, so alpha over x0 minus alpha over x0 plus x final, then multiplied by 2 and divided by m. This is what we obtained for V final. So if we substitute the values of alpha and m and x0 here, we obtain 2 times 0.8 divided by the mass 0.5 kilograms, 1 over 0.2 minus 1 over 0.2 plus 0.4 is where we want to find the speed, square root. All right, so we take the square root of this, and the final answer is 3.27 meters per second. All right, so we're given a conservative force, alpha over x plus x0 square, parentheses square. This is the spatial dependence of the force. Alpha and x0 are some constants. We want to know the potential energy function for this force, provided that the potential energy is 0 at infinity. So we use the work potential energy theorem for a conservative force. The minus the work done by the force in moving from 0 to x is the change in the potential energy. So let me write here. This is basically work potential energy theorem for a conservative force. So to perform the integration, we change variables from x to y here, and we perform the integration between the limits when x is equal to 0, y is equal to x0, when x is equal to x, y is equal to x plus x0, so between these limits. So we obtain potential energy at x minus potential energy at 0 to be alpha over alpha times 1 over x0 plus x minus 1 over x0. We have the condition that the potential energy is 0 at infinity. So u infinity minus u0 is minus alpha over x0. So this is our u0 is potential energy at x equals 0 is alpha over x0. So therefore we find that this gives us the function u of x, alpha over x0 plus x, and u0 is indeed alpha over x0, and it is 0 as x goes to infinity. Now, if we move an object with mass 0.5 kilogram from rest at x equals 0 to x equals 0.4 meters under the influence of this conservative force only in the positive x direction, the change in the mechanical energy will be 0 because we have conservative forces. Therefore, we have conservation of energy, of mechanical energy in the system. And the change in kinetic energy from 0 to 1 over 2 mv final square, change in potential energy from alpha over x0 to alpha over x0 plus x final, where x final is 0.4 meters. This equation gives us delta k plus delta is equal to 0 v final in terms of alpha m x0 and x final. If we substitute m 0.5 kilograms and x final 0.4 meters, we find the final speed to be 3.27 meters per second. Now this is the answer is given with three significant figures because this has three significant figures, this has three significant figures. So that's the minimum number of significant figures given in the problem.